Systems. We've been working with Hadoop in HBase since 2008 and since about 2009 and early 2010 using it in production. And this talk will go through our OLAP solution, simple OLAP solution that we build on top of these technologies. So we're going to explain a little what we're trying to solve. The term OLAP is very well defined. It has a lot of literature, a lot of people actually researching it to a much deeper level than what we're trying to solve. However, ours, we think it's an OLAP system nonetheless, but it's just a subset. So we're trying to explain what exactly we're trying to solve. Then we're going to go through a description of the entire system. Hopefully this will be a more engineering, this talk will contain more engineering details. And we'll go layer by layer from the top level view to internally to see how it works, how we're using Hadoop, HDFS, MapReduce, and HBase, and what we're doing to minimize latency. So in a nutshell, we have this low latency OLAP system, which uses Hadoop DFS to store input data like log files. The processing loop of the system, it's built using some MapReduce jobs, which basically take a cube description, and we process it by pre-aggregation using Hadoop MapReduce, storing the results into statistics output HBase table. Afterwards, users interact with the system by querying a server, which basically scans these HBase tables, applying the filters, rollups, drill downs, any kind of simple OLAP operations that you can think about, and returning the result. Before we move on, it would be interesting to see a show of hands. How many of you here have worked with SQL? OK, that's great. And OLAP systems? Still great. What about, I know most of you have worked with Hadoop since you're at the Hadoop Summit, but what about HBase? How many of you have been running or working with HBase? OK. So basically, I'm going to move really fast through this with this vocabulary that I'm trying to explain. And I'm only doing this because these terms will come up over and over again during my presentation. So basically, we have a set of input data like web analytics files or sales events or any kind of data. And this data, basically, you can split it into two big parts. Basically, you get numeric data, which are metrics or measures, like sales or number of visits. And this data is tagged with a set of metadata or labels. And these are called dimensions. These characterize our data and put it into a bucket or another bucket. Time is a dimension, or any other metadata your rows or your events can contain. Basically, what you want to do is answer all kinds of questions, which all boil down to a fundamental operation of viewing the metrics by any combination of dimensions. Here's some simple examples, since most of you are familiar with SQL, about some simple OLAP queries that we can do, like rollups. Rollups basically decreases the cardinality of your data. Having, 50 sales events, if you only consider a couple of dimensions or only one, like the country, you can roll up and sum or count the rest of these rows, which essentially become one. Another type of really important operation is slicing. Basically, what slicing means, it says, take my data, discard any kind of rows which don't fit into a certain pattern or where a dimension doesn't have a certain value, and with the rest of the data, apply the same operations like rollups or just getting it. Another really, really important operations that users usually want to do is they want to order the data. And why do you want to do that? Because you want to see which country you have the most, in which country you sell the most, basically. Now let's go and take a look inside the system, layer by layer, and see how it looks like. It's pretty simple. And once we go down, things will start becoming a little bit more complicated. But basically, our system is running on an unusual Hadoop and HBase cluster, which we collocate for data locality on the same machines. So you've got a cluster of 10, 15, 20 machines using, running Hadoop data nodes, test tracker, name nodes, job tracker, HBase region servers. Then our software comes on top of it as a MapReduce job. and the query server component, which users typically query through a load balancer to get back the analytics results. Now, how do users interact with the system, and what's actually going on? This is the entire data, simplified data flow of data through our system. Everything starts with users creating what we call a reports definition. This is basically like an OLAP cube specifying what questions you want to answer to. This is encoded as a simple JSON file, which contains, again, these concepts of reports, dimensions, and metrics. Data comes into a system, that's through an external process, which we won't go in about here. Our system can handle either simple basic log files or Hadoop input files, or more often we use HBase as a data warehousing mechanism. And I'm going to go into a little bit more detail later on why we do that. Once data is in the system, we have the MapReduce job, the processing job, which we call the superprocessor, which basically takes this entire data set or a part of it, pre-aggregates it, and writes it to a statistics output table. Then users, as I said, use the query server, which basically scans this table to get the data. Why does this work? What's the fundamental simplifying assumption that we make, which works in most of the cases that we've met? In most of the cases, you need to summarize the data. You don't need to look at 1 billion, 2 billion, 3 billion data points at any one time. Also, if you have a really rich event set with a lot of dimensions and you can split it any which way you want, you don't usually need to look at all the dimensions at the same time, because any change in the system will make things very, very hard to correlate. You get rid of one, and the rest set of big dimensions will skew your data, and you won't be able to get any intelligence, any understanding out of it. And finally, not all queries are used with the same frequencies. This is really, really important. What we typically see is that users have a set of queries that they use all the time, which must run really quickly, and the set of queries that they use for data to inspect the data and see what's going on. But those are typically not used with the same frequency. So that leads us to a problem that comes up in all areas of computer science. If you think about the user's experience, you can either optimize the time the user has to spend getting back results from an analytics system, or the space. And each one comes with its own set of pluses and minuses. In most cases, if we want to optimize time, we apply this operation of pre-aggregation, which basically reduces the cardinality of your data set by orders of magnitude, which leads to really, really fast queries and efficient reads, which are basically independent of the size of the initial data set. But it's also pretty inflexible, and you get the latency added by the processing layer. And you get a combinatorial explosion in some cases. What does that mean? The combinatorial explosion is what happens when you have dimensions which have a huge number of values, like tags. For example, if you think about delicious, the set of tags in delicious. If that were one of your dimensions, you'd have a huge set of dimensions, a huge set of pre-aggregated rows. On the other hand, you can just query the initial data set, and that's the most flexible that you can get. But it's really, really I/O and CPU intensive, because in the worst case, you basically need to scan through the entire data. So why not do both? Our system, users of our system can choose whether they want to tune, they want to pre-aggregate more and get rid of a lot of dimensions for some really fast queries, or add more dimensions to the pre-aggregated data, which basically will translate to exactly the same as runtime aggregation. Basically, this works in a SQL database or a relational database exactly like normal SQL queries. If you want to optimize them, just create some materialized views. So what's our solution? This is basically what's happening inside the entire system. In the processing step, we pre-aggregate all the report definitions that we know beforehand, and we create an indexed HBase table. Then at query time, we use the indexes to get to the data fast, and we can also perform extra aggregation or roll-ups or slicing at runtime. Doing this, we use exactly the platform strength, which is parallelism, which is given to us by Hadoop MapReduce, and fast access and natural key ordering in HBase. Just for those of you who haven't used HBase, this is some really minimal detail so you understand what's going on. Basically, in HBase, HBase, the Hadoop database, is a columnar data store where data is stored in tables. Each row has a key and any number of columns. This is really, really important. So think about HBase as like a quasi-infinite Excel table. So tables can be both long and wide, which is really, really important if you want to group some events and store them on a single row. Also, the most fundamental property of HBase is that clustered indexes are built in. Inside a table, the rows are ordered in an absolute order by the row key, lexicographically by the row key. If you insert new data and then you get it back from HBase, it's going to return the rows in exactly the order of the row key. Finally, as I said, it's like an Excel table, but tables are sparse. So basically, you don't need to store null values. A column that doesn't exist, that's a null value. It's well, it's a bit more complicated than that, but at the core, most operations use the row key. So you can either get some data from a row or put some data to a row, and these functions both use the row key to identify the row. Another fundamental operation is you can scan a range of rows. Why does this make sense between a start row and an end row? Why does this make sense? Because the rows are ordered by the row key. So that means if there's an ordering relation, we can say start from row AA and get me all the data until row BC. So the first thing that you think about is that why don't we use the row key as a built-in indexing mechanism? Here's, for example, again, this will be really, really familiar to those of you that know SQL, about what a SAS base, that's how our system is called internally. I wanted to call it Panthera, but didn't come up. So here's an example of a SAS base, what we call a report, as compared to a SQL query or a materialized view. Basically, you specify exactly the same things. You can map them one-to-one with the SQL query. You've got dimensions, which represent the elements in your group by clause. And then you've got metrics, which are stuff that you want to select. And the dimensions also, you can select them. You have what we call transport dimensions, which don't impact the data in any way. You just want to attach them to the output results. And finally, you can specify some sorting using a specific metric or dimension. The having or where clauses are not specified here because in this step, when we create the report's definition, we don't know exactly what we'll want to query. So that's all done at runtime. So again, and this is really, really important, the same concepts come up over and over again. The report configuration is the central part of our system. It's used, all the components in the system, the import step, the process step, the query step, load the set of reports configuration and use it to make sense of the input data. The report configuration, it's pretty simple. It contains a list of dimensions, a list of metrics, and a list of reports which basically have this format, containing the same dimensions, a subset of dimensions, a subset of metrics, and eventual sorting. Also, apart from this report configuration, users can choose to implement and override their own dimension and metrics classes. And this turns out to be a really, really handy mechanism of injecting some flexibility into the system. Again, we're going to spend a little bit more time here. So what's our solution? Basically, this is the, if I could end the presentation after this slide, that would basically be it. What's the solution? Given a set of input data, which contains some metrics like sales, which are tagged with some metadata like dimensions like date or country or city, and, oh, that's not right. And given a set of reports which are overlapping a bit, but given two reports, one of which groups the visits by city, by country and city, and the other one, gives us the total sales value for, for a certain day and a certain country. What this amounts to, after the processing loop, we will fill the statistics HBase output table with some rows that look a little bit like this. And I'll go through and explain what's going on. Basically, what this does is pretty simple. For all the input rows, for all the reports, take each report's definition, group it using only the specified dimensions and metrics, then write a row in an HBase table which contains something like the report identifier, then the list of all the dimension values, and finally, just add up and write the metrics to a column in the statistics table. Why does this work? So what's going on at how can we use that? Again, because the rows in an HBase table are ordered in a natural order, that basically gives us a built-in hierarchical filtering mechanism. So, for example, if you've got something like a date dimension, which is composed of year, month, and day, and then you've got the country and the city, let's say I want to look at all the data in 2012. Well, that's simple. That translates immediately to a simple HBase scan, which just says, get me all the rows that start with 2012. The same, let's say you want to drill down and look for the month of May. The same thing, just create a new scan that says get me all the rows that begin with 2012 / or another separated 05. And again and again and again, for all the dimensions in your reports, you can filter and do roll-ups or slice to any level that you want, given that you have specified the dimensions beforehand. So this property of HBase of having the rows ordered by row key, is really important. That's basically the core of the system. We can use and set dimension values which translate directly one-to-one to HBase scans. What about sorting? That's, as I said, that's another really important operations. You want to see which country have made the most money for your, your online shopping system. Well, it's pretty easy. We can use the same mechanism. We only added dimensions to the row key up until now. But what you need to do is simply add all the metrics that you want to sort by to the row key in a way that reserves the ordering. For example, order by desk that pretty much gives you kind of like a top query, like give me the countries where I made the most money. To do that, you need to encode the metric there are other formulas, but one that works really well is, for example, having max value minus the value of the metric. And when you represent this as a string, it's going to sort lexicographically in descending order automatically. Okay, now let's go through all the components of the system and see what we're doing to minimize latency. Latency is the absolute killer in an analytics system. All of our users at least, have asked us what's the latency until I get some results. What do I mean by latency? Latency is the total amount of time until an event is born somewhere, whether a user clicks on a web page or somebody starts up Photoshop Touch on their tablet, or some other event happens in some place somewhere, until a user that's interested about that event can see it and answer some questions about it. If you think about it, usually what we see. You can split the latency into these components. You've got an import latency until since the events are generated into a system, until they get ingested into our processing system. That's usually a latency. If you can get rid of it altogether, that's fine. But you have to account for it. The other one is until the events are in the system in HBase warehouse table, then they get picked up by the processing loop for pre-aggregation. That's another latency. Then while the pre-aggregation loop runs, that's yet another time that increases the latency. And finally, again, we can choose to have really, really fast reports by pre-aggregating more, or have more complex reports which lets user delve in however they want. But then you would have a considerable query latency because you would have to scan a lot of data. So when you talk about minimizing latency, we have to look at minimizing each of these components. To minimize the import latency, the best way to minimize any kind of work is not to do that work at all. So basically, the most important thing we can do is not import data that's already in the system. So what that means, or only import the minimal set of changes. Basically, here we use some custom MapReduce input filters if we use log files for input, or we just use we specify start and stop rows for the data warehouse HBase table input scan. This is really interesting. We have a couple of input filters for MapReduce, which basically they work together and they say they give you a result which looks like process files from a certain date range only once. What does that mean, only once? We have all kinds of integration. Integration is a big part of our system, and we have all kinds of use cases where we have log files which are not rolled and are updated every time. So we actually copy them, but the log files are live. New data is actually being written to the log. So we need to see whether that log has been modified or not using, for example, a checksum, a control checksum. Another thing that's really important is that usually there are two antagonistic ways that you can optimize the system. You can either optimize it to work fast for incremental updates, incremental processing, or you can optimize it to run really, really well for huge input data. So for example, we have clients which say, yeah, that's fine, your system is awesome. How long would it take me to ingest and process my 5 years worth of log data, like petabytes of log data? And to optimize for that, one of the most important things we can do is minimize map task overhead. What does that mean? We have use cases where we have to ingest or process a huge amount of files at any one time, like 400,000 files, 500,000 files. It would be too much to rewrite them into a format or a form that's good for HDFS. HDFS is really good at dealing with bigger, so less files which are bigger than a huge number of small files. By default, Hadoop MapReduce, if you give it, if you run a job with 400,000 input files, it's going to create 400,000 map tasks, which will basically, if you run a MapReduce job on that, like 80% of your time will be spent in the reduce copy phase when the results are copied to the reducer. So what we do here, both for log files and for HBase warehouse format, is we stitch multiple input splits, whether they be files or HBase regions, into the same map task. That's another really important thing. HBase by default, you can use it as a live system, so you can write data to it. But again, for the use case of huge bulk imports, you need to use H-file output format. What this is, it's a Hadoop MapReduce output format that basically creates exactly the same data files that HBase would normally create during its operation. So basically, you say to HBase, here's a table. Load it up and use it. It's already written. The data is already there in the format that you need. You don't have to do anything else to it. That's about from 100 times to 1,000 times faster than pushing data using the API. And if you do that, that presents its own set of interesting problems. The first and foremost is there is no shuffle steps. So you have to use in your MapReduce job a global order partitioner. which solves a problem, which means the data will be sorted for HBase when it loads it. But on the other hand, it's a bit against to how the real world runs, because the data grows over time. So if you're using something simple like only the date to estimate the output partition, so for example, to say if you want to import 2 years of data, I'll just create 365 times 2 regions, so 1 region per day. But the problem with that is that the beginning regions will have like 50 megabytes of data, whereas in the end, you will have huge regions like 5 gigs of data. So another thing that we've worked really hard on is having a way to estimate output partitions based on input data size. That's usually a pretty good heuristic, because if you're doing warehousing, the more data you ingest, the more data you're going to write. And if you ingest like 5 gigabytes of data for a single day, then it makes sense to create 2 HBase regions for that day, not only 1. So for that, we have the file size date partitioner, which basically communicates with the input filters. And what the input filters do is they let the files come into the Hadoop Map reduce computation. And as a side effect, they write the size of these files and the name of these files into an HBase table. This HBase table is then queried and injected into this partitioner, so we can rebalance regions based on the actual file sizes. OK, so that was import. Let's move to processing. So again, what does processing do? Just the simple stuff that I showed. It just creates an indexed HBase table with everything we need in it. So that involves reading the input, whether it's files, tables, or events from another system, pre-aggregating them, and generating the tables. If you want to think about SQL operations, that does group by eventual aggregate functions and ordering. The processing in our system is implemented as a single MapReduce job. To minimize that, again, you have to split it by pieces and minimize each MapReduce step. Read, map, shuffle, reduce, everything. For reading data, again, how do you minimize work? You simply don't do it. So we've spent a lot of time doing what we call incremental processing. What does incremental processing mean? Basically, if you think about something like visits on a website, visits last for a single day, right? So once you do processing for up until a week ago, there's no way that new data that comes into the system could affect the analytics that were built for a week ago, a month ago, a year ago. So what that means is you don't need to reprocess that entire data set. But you need to have a way of differentiating between open and closed data. Open data meaning data which could influence your current analytics pre-aggregations. Of course, we use all the HBase scanning options like caching and batching, so we minimize the number of round trips to the HBase region servers. And finally, before processing, we ensure that HBase table regions are evenly distributed inside the cluster. The superprocessor that's actually called the superprocessor class. It's a one-shot MapReduce job. Again, what the processing loop does is just like a game inner loop for all the data, for all the reports, emit all the pre-aggregated values inside a single MapReduce call. I wouldn't show you the code even if I could, because it's ugly. It pretty much reads like C code. There are no allocations inside this MapReduce job. It's retardedly simple. There are no system calls. There's no logging. We have some very intricate mechanisms of detecting errors inside this MapReduce job, because there we can't have any logging. There are no transformations anywhere. Everything is used either byte buffers or byte arrays. We store data into arcane representations between the map, combine, and the combine and reduce steps to minimize the I/O each step of the way. And again, there are no memory allocations inside this job. It's built to be really, really, really fast. It might take a long time for smaller clusters, but what I mean by fast is basically we want it to run as close as possible to how a bare metal program would run. What about query latency? Well, that's That's another really interesting problem. We have a simple thrift server, which is called the report server, which users query to get the data, and they get back something like JSON results. There's not much to do here. Data is already processed or pre-aggregated in most cases. Of course, you do have the use case where you have huge number of dimensions in a single report, so that's going to take some time. Related to a SQL vocabulary, at query time, we do filtering or slicing like where clauses and extra group by. So what does that mean? If you have a pre-canned report definition using 5 dimensions at query time, you can only request 3 of those. So that's going to get all the rows, discard the 2 dimensions, and then roll up the rows that aren't distinct anymore. This is a really interesting problem. What the query server does is calculate an optimal set of HBase scans. What does optimal mean? Well, in some cases, we might decide that we'll do a single scan and then discard a bunch of rows from that before doing the calculation. In other cases, we want to do like 50 small scans and then use all of the results in those. Using the slices and using the where filters, the queries that the user specifies, this report server creates the prefixes and creates some scans with starts and stop rows. There's a lot of stuff that we're doing to minimize data. Of course, it can perform extra rollups and sorting. In conclusion, this is pretty much what we built. I guess the most important thing is that the report configuration is in the core of the system. The query server, the MapReduce job, the super processor, all are really, really, really thin layers. All the functionality is actually delegated to these dimension and matrix classes, which the user can override completely. They can override serialization or aggregate function. You can have metrics which are actually alive, metrics or dimensions which are actually alive, like only return the value 1 if an event has a certain property, and 0 in all other cases. So as soon as we see our users having emergent patterns, like for example, what do you call them, averages. They were implemented by a user, and then we integrated it into our system using those custom definitions. It's really, really flexible because then you don't have to duplicate the code to move everything out of MapReduce. We're experimenting right now with real-time analytics where the entire processing loop is using Storm for processing, not MapReduce. We're running in production with about 5 clients right now. Of course, there's still a lot of more work to do. I haven't talked anything about productization, operations, and there's still some programming required. That's pretty much it. Hopefully, I had enough time to go through the entire system. For more details, just go to our website or send me an email. And I do think we have time for some questions. Thank you.
And actually, that's interesting, the way you arrange the row key. I was wondering whether you explored anything about the secondary indexes, for the metrics and the dimensions.
Yes, we are exploring that more. So the question is if we are exploring something related to secondary indexes. And the answer is yes, we are exploring that using the new coprocessor functionality that's in HBase right now. So basically, the way we think about it is like moving some secondary indexing, like for example for sorting, inside an HBase coprocessor, which writes its internal HBase table, so we don't need to query it to worry about anything.
Okay, thank you.
The question was whether Omniture data is stored like this or it's in a different system. Omniture data is in a different system. We were already in production with some of our use cases when we acquired Omniture, and we are talking to them for some use cases, but right now they have their own stuff for the moment.
Hi, I have a couple of questions. The first is the data volume. So on the reports you're currently running on your system, on the biggest one, I'm taking the biggest one example, on how many rows are stored for that report in the HBase side.
Yeah. So for example, for a web analytics system that contains a table about 400 regions, which translates to about 800 billion visits. So that's visits, not individual hits. Each visit contains more hits. The statistics table is aggregated to about 10, 15 regions. I don't have anything more more specific than that. So it really reduces the size of the output.
So when you say the statistics table, you mean the pre-aggregation
table?
Yeah,
the pre-aggregate table.
So the second question I have is, you mentioned in the processing step, you launched a MapReduce job to pre-aggregate the data. And after that, you have a query issued by the client to query on the pre-aggregate data. Is that still a MapReduce job, or?
No, that's an actual server that just goes to the HBase table and serves the data live from the pre-aggregated table. So what's batch is we write pre-aggregated results, but at query time everything is done in real time basically.
Okay, so both the MapReduce job in the processing step and the query from the query server, they both use the scan as the fundamental operation to hit the HBase.
Yeah. Well, the pre-aggregate, the MapReduce jobs mostly does writes into the HBase table. The query scan does reads by scanning the output table.
Okay, and so one last question. I'm sorry. The first step is import step. You import the data from the clients, and how often you import the files from the clients?
Okay, so in our current most advanced production use case, we import data every 2 or 3 minutes. Then the processing loop takes over, and it's another 4 to 5 minutes. So basically, we've currently have something like 8, 9, 10-minute latency for a web analytics.
Okay,
system.
so then how you manage compactions?
I'm not sure I.
For example, once you load data every 10 minutes or every 10 minutes, so there will be new files, or for example, you have 100 regions, there will be 100 files. How we manage compactions?
And I think we have another question here. Really shortly, the way we do it is in the warehousing table, we use the date as the beginning, the beginning of the row key. So that means we won't write data spread into all the regions, just a couple of hot regions at the end. So we can handle the splitting and the compactions for those couple of regions every couple of minutes.
Thank you.
Hi, I'm Christopher Dean. I wondered if you ever had cases where data corruption or whatever that made you have to roll back, like 2 months ago, someone said, oh, that data I gave you, that was junk. Please, here's the good data.
Yeah.
What do you do then? And
we cry.
We cry.
We cry like little girls, and then we just reprocess everything. That's another thing that, I'm sorry. What we usually do, but that's more like an operational detail, always try to keep the initial input data. That will allow you later to clean it up or fix it into some way, or re-import it into the warehousing layer, and have some more stuff that fixes it into.
Do you have a manual process where you delete, the aggregate data and then you just rerun?
Yes,
everything?
we can delete. It's not it's manual. We can delete aggregate data for a report or for any combination of report and dimensions, just like the query. Instead of query, you delete. That's
cool. Thanks.
Yeah. I'm sorry. You.
So what bottlenecks are left?
What bottlenecks are left? That's real time. Real time. That's what we're focusing on right now. I mean, not minutes, seconds. 5 seconds is too much for some of our clients. So that's what we're working on right now. Inside the system, you mean like at the physical level? The one we've optimized and that's bitten us in the ass up until now was I/O and networking, disk and networking. Basically, we haven't had money or time to experiment with stuff like SSDs. We typically run small clusters of super beefy machines because that's what we can get due to budgeting and stuff like that. So that's what's been biting us.
So do the applications involve reading
I'm sorry, could you?
So do the aggregations involve aggregating against the historical data stored in HBase, or do they complete it in the superprocessor itself?
So the superprocessor is pretty agnostic. If you give it 3 years worth of data, it's going to pre-aggregate those 3 years worth. If you give it a 2.
But you get data for the last few minutes.
Yeah.
And do you aggregate it against historical data which is stored in HBase?
Yeah, that's the thing. We don't need to do that. Actually, what we do every couple of minutes, because it's a web analytics system and the visits close every 3 days. So what we do is we process 3 days behind. Other than that, it can't possibly affect the older analytics data. We store the output in a window table and then just use both tables to do the queries. I think one last question.
So do you support roll-up or drill-down queries on non-additive metrics?
No. That's non-edible measures. Yeah, that was something that we've worked like half a year to figure out how we can do it. It's a really, really hard problem. We're not solving it correctly. We're solving it, I think, as well or as bad as anybody else. We use stream counting for something like unique users. We lie, basically, like what's unique, daily unique. Daily unique is not unique. So. That's fortunately, we haven't had to do more advanced use cases. We do have some experiments that can fix this issue, but it's still a long ways, and we still need to work on it. Okay, I think that's all the time we have. Thank you.